and planets are passively cooling in the disk, accreting as they cool, then they're going to have a cooling time close to their disk lifetime. So if you say, I have a Kelvin-Helmholtz time or a cooling time that's comparable to my disk lifetime, a few million years, and my planet's bound by the Bondi radius, then I can roughly accrete 10% hydrogen helium over that time. And that's a reasonable inference. But the problem comes is because I have this planet, it's embedded in the disk, extends out to its Bondi radius, and it has a cooling time of a few million years. But as I just told you, the disk goes away very quickly. It goes away on a timescale much, much quicker than this million years. And because these planets have a cooling time of only a few million years, they can only contract or thermally evolve on a timescale that's comparable to that. So if I say I take my planet and then I just rip away the disk on a timescale much, much closer, shorter than this million-year timescale, it can't contract or do anything. But I've changed the outer boundary condition. I've gone from a pressure-confining disk to a vacuum boundary condition. This, as I said in my project presentation, makes the planet very, very unhappy. It makes it so unhappy that it probably lost a referendum in the UK. So this is our wonderful Prime Minister that has done this to our country. He gets very, very hot and unhappy. He now has no people to hold him in. So he flows outwards. He launches a wind. And this is just a response to what Ruth said in her talk. We've gone from a pressure-confining boundary condition to a vacuum boundary condition. You cannot support these atmospheres. You can't have a hydrostatic atmosphere out to infinity. It just doesn't work. You've got to launch this wind. So the question is obviously, how important is this wind, and is it dynamically important? Is it important for the planet's evolution? So my argument is yes, it's going to be very, very important. So what I've done here is I've plotted the mass loss timescale as a function of the planet radius in terms of this Bondi radius. And what you see is the planet's sort of born out here. When it exits the disk, it has a radius close to the Bondi radius. You can see that the mass loss timescale is very, very short if you're this big for this type of process. And it doesn't really get long comparable to the cooling time of the planet, which is a few million years, which is this natural evolution timescale. So you get down to 0.1 Bondi radius. So you're really going to only shut off this process once your planet radius gets down to about 0.1 Bondi radii, and the mass loss timescale is longer than the cooling timescale, and the planet cools away. And this mass loss becomes unimportant. So you're obviously going to have a decent length of time when the planet starts off here and it's got to evolve down to here before it stops losing mass. And this can actually have a dramatic effect on the planet's initial mass fraction. If you just took a result from a standard planet formation calculation that didn't include this, you might end up getting a very, very wrong initial mass. And you can actually make a lot of progress by just thinking about in terms of simple energy arguments. So you say that my planet initially has a gravitational binding energy that's close to this. This is just the g times the mass in the core times the mass in the envelope divided by the planet's radius, which I parameterized in terms of some number, alpha, which is less than 1, times the Bondi radius. But I said this process stops when the planet has a radius of about the 10th of the Bondi radius. So this is the binding energy when this mass loss process stops. And I know how much energy I have to lose by throwing this material out to infinity. This is just taking the binding energy of the material I had at the start minus the material I had at the end. This is the amount of material I must throw off, times some characteristic radius, which I'm going to, for the sake of argument, set to the initial radius of the planet. And you say that the dominant process that drives this energy is not irradiation from the star, but just the internal luminosity of the planet itself. So these are the only energy terms I care about, and then you can solve for the mass fraction and final mass fraction in terms of the initial mass fraction. And you'll see that the final mass fraction is much, much smaller than the initial mass fraction, about 10%. So you don't have to take my word for it. These simple physics arguments work out. You can run some simulations. So these are MESA simulations that we ran of this process to try and answer some questions that I couldn't answer with that back of the envelope calculation. So my planet is being irradiated. I do have some energy input. Is that important? Do I lose any energy during this process? And could I transport energy not at a convective to radiative boundary, but to a convective advective boundary? So you can see this is the kind of profiles we got. So you start off up here, close to the Bondi radius. You launch this whole wind that drives itself from the planet. Internal luminosity is driving material out of the planet. It removes material, so my planet begins to shrink. And then I shut off this process entirely where I don't have a wind now, and the planet is just contracting as a normal planet. So you can look up how this evolves in the envelope mass versus planet radius plane, again scaled in terms of this Bondi radius. And you see that the planet starts out at 1 Bondi radii, and this mass loss process basically gets shut off entirely at 0.1 Bondi. This is what is expected. And again, you've started off with envelope mass fractions in the tens of percent, and you've ended up with envelope mass fractions in the few percent. So I've lost maybe 90% of my initial mass. The other thing you can look at is the final properties. So this is my planet radius as a function of core mass. The different symbols here basically correspond to different orbital separations. So as you can see, the different orbital separations are not lined up at the same place. They all started with the same initial mass fraction. This means that irradiation does have a small impact. There is a small impact from adding energy into the planet from irradiation. But it doesn't have that big of a difference compared to the total mass loss. So the open symbols have gone from this solid line, a 30% initial mass fraction, down to these few percent, 3 or 4%, and the solid symbols have gone from this dotted line, an initial envelope mass fraction of 10%, down to these percent and lower. So most of the energy for this process does come from the internal luminosity of the planet itself, but there is a small influence of irradiation. And we tend to find that the planet final radius always tends to be smaller than a roughly 3 Earth radii. This is perhaps the most interesting part of this process, and probably the most unexpected, is this process has a very, very strong influence on the initial entropy content, or the initial cooling time of the planets after this process has happened. So I said that these planets have initial cooling times of roughly a few million years when they're in the disk. If nothing dramatic happened to them, then that should be the same after the disk has gone away. But we find that the initial cooling times after this process has finished tends to be very, very long, a few 10 to the 7 or 10 to the 8 years. Now the reason for this is that planets typically cool because they have a convective radiative boundary. But because I have this strong mass flow, what happens is the advective energy transport in this flow from the base of the convective zone overwhelms the the transfer of energy by radiation. And I actually just completely release this radiative bottleneck at the convective radiative boundary. And I actually just advect huge amounts of heat out of the interior and cool it down dramatically. So it remains to be seen whether this kind of process could have important evolutionary effects on the planet. I will add one thing, which is perhaps possible. I don't want to emphasize this too strongly, evidence of this process occurring. So this is from a paper where we looked at the initial properties of Kepler-36. This is a sort of puffy planet that has a few 5-6% hydrogen and helium. And we evolved the whole planet back in time, just to the moment after the disk had gone away. So at the end of this process I'm talking today, including photoevaporation and thermal cooling, and asked what its initial properties were. And in order to fit the data, including that evaporation and cooling model, we required the planet to start with an initially long cooling time. And the reason for this is because these planets are photoevaporating and losing mass over time, as you heard several times during this week, you need to add more and more mass to the initial planet, so you have the same amount of mass when you reach the final stage we see today. But if you add more and more material, and you add more and more entropy into the planet, you make it hotter and hotter and give it a shorter initial cooling time, you eventually reach the point where if you were down here with a short initial cooling time and lots of mass on the planet initially, you were actually completely unbound. at zero time. You weren't a real planet. You were just a sort of fuzzy gas ball that was escaping from a core. So Corentin has actually agreed to do a project looking at more planets, not just Kepler-36c, but a few more. So maybe he will tell you whether this is a freak accident or more of a trend at the end of the 6 weeks. So hold your breath. And I'll end with one thing, which is, it's sort of a project advertisement, but I guess everyone's decided what they're doing now, so maybe this is my project for the 6 weeks. Those clever among you will have noticed when I showed this plot of M mass fraction as a function of time, the time scale over which this mass loss occurs is not long compared to the disk dispersal time, it's actually comparable to the disk dispersal time. So this means the assumption of just taking a planet, removing the disk, and then letting it evolve as it would like to, launching this wind, is not quite true. The physics that occurs while the disk is going away is going to be important. And there was a nice paper by Akuma and Hori in 2012 where they looked at what happens to a planet that's embedded in the disk. You force it to be hydrostatic, so you don't allow any wind to occur, and you let the disk disperse slowly. And that, in that case, because you're maintaining hydrostatic equilibrium and your amount of material in your disk is going down, then your planet mass must go down. And you evolve that all the way till the disk is gone, and you find there's a little bit of less mass than you started out with. So what I think is going to happen, which I will maybe work out in this project, is that will happen when the disk starts to go away. You'll start to get this sort of time where you hydrostatically readjust to the new disk, but eventually the disk is going away so fast that you can't maintain that, and the wind just blasts itself through the disk and launches, and then you enter this boil-off phase. So the buzzer is gone, so I better finish. So in conclusion, many of these close-in planets have hydrogen and helium envelopes, so they must have formed in the disk. They must have gone through this rapid disk dispersal phase. This rapid change from pressure confining to vacuum boundary conditions necessarily leads to mass loss, and this mass loss can be pretty significant. It's driven by the internal luminosity of the planet itself, and this has pretty strong cooling, pretty important implications for the cooling of the planets, and maybe leads to premature aging of the planets over time. So, thank you. I'll end there and take questions. Yeah. Yeah.
So I'm wondering if a similar thing happens, or is maybe that's a different mass regime?
So you're right that there are two mass regimes. So everything I've said today relies on the fact that the envelope mass is less than the core mass. If you're in the opposite regime, where the envelope mass is higher than the core mass, then this process doesn't occur. So it depends where that happens in the gap opening stage, and it also depends, as you know, critically on how fast the gap opens. If it opens slowly as the planet's accreting on a planetary accreting timescale, then the timescale for the gap opening and the pressure release is comparable, I would imagine, to the other standard evolutionary timescales of the forming planet. If gap opening is more vigorous, say, and happens at a specific point or is much faster, then I could envisage something like this occurring, provided the envelope mass is less than the core mass. I was not around then. So. So that's an excellent question, and one I do think about from time to time. I think the key point is the exoplanets we see close to their stars have gas, and that tells me they must have formed when the disk was around, but the terrestrial planets in our solar system do not have gas, and that would tell me that they did not form when the gas disk is around. And that might point towards why people start to think that terrestrial planets grew out of a planetesimal disk rather than occurring in the solar nebula. Yeah. Yes. So it's a curious point that I think that the fraction is 60 or 70% of planets, of stars contain a planet that's shorter than 100 days and smaller than 4 Earth radii. And they're basically all this standard planet. So that would tell you that we don't have a planet inside Mercury that's 3 Earth radii. So that tells you that our solar system is different from a formation scenario than the standard exoplanet system we're starting to see today. And if we can untangle that in terms of formation models, then we might start to learn something very, very useful.
Are the so-called super puffies abundant enough that you worry about them in a scenario like this?
I do worry about them. So Jonathan is right, the super puffs. So maybe if people don't know what super puff or the term Eve Lee is characterizing, I think she was the origin of this term. Superpuff? So the superpuffs are these up here. So these are a few Earth masses, but have radii of 7 or 8 Earth radii. So have envelope mass fractions of 30%. So if you take my argument that you must have lost 90% of your initial mass, then these would have been in the runaway phase with 200% hydrogen helium to start with, and you would have never gone through this process. But I think they're rare enough that they do not they're not a significant population, and I don't think we know at the 10% or maybe 20% level that every single disk that formed went through one of these rapid disk dispersal phases. All we know is the classic astronomy problem. We know we can count, and we know what most things do. So that's one thing. The other thing is the superpuffs tend to be at much larger separations than these. And most of our information for disk dispersal tends to be dominated to more shorter radii. People like me and others have models for how this disk dispersal process should take place, and it is radius dependent, that the rapid dispersal phase is dominated to smaller radii. So that may be part of the story as well. But these superpuffs are a very interesting exception, both for this process and for planet formation in general, and for planet evolution.